All right, so today we are going to start our journey through thermodynamics here. And so to start us out, the first law of thermodynamics. So basically, this law states that energy can neither be created nor destroyed, only converted from one form to another. So, two types of energy that we really deal with here are kinetic energy, and this is the energy of moving things. And then we have potential energy, or the stored energy, that is the result of attractive and repulsive forces. So, probably one of the best known potential energies is gravity. So, as an idea, that is a potential energy, right? Because when you lift something up, you are storing gravity energy in it. You release that object, it falls, and you're converting the potential or stored energy into kinetic. So, in thermodynamics, we divide the world or universe into two things. We have the system and the surroundings. So, the system, that is a limited, well-defined set of objects. So in chemistry, it's often the products and reactants of a chemical reaction. And then we have the surroundings, so everything else in the universe that is not part of the system, which means the system and surroundings together make up the universe. And so systems, we can divide systems into three different types of systems. One is an open system in which matter and energy can be exchanged with the surroundings. Usually when we talk about energy in chemistry, we're talking about heat. So matter and heat can be exchanged with the surroundings. Closed system, only energy can be exchanged with the surroundings. So matter is contained, it can't go anywhere, but energy can still be exchanged. And then an isolated system where neither matter nor energy can be exchanged with the surroundings. So a completely sealed or isolated system. Now, one particular type of energy that we want to describe here, because it comes up in thermodynamics, is internal energy. So this is the sum of all the kinetic and potential energy in a system. And as such, it's difficult to define. We'll almost exclusively be dealing with changes in internal energy rather than a static value. Okay, so another thing that we have to define here is something called a state function. So what this is, a property of a system that's determined by the current conditions of the state of the system and unaffected by the path that was taken to arrive at that state, right? So something like some examples that I tend to see are like if you, oops, why is this not writing? Come on, bear with me for a moment. Let's write here. Why are you doing this to me? There. So let's say we've got a mountain, right? Great mountain. We want to get up here, right? But right now we're starting down here. Me, you can tell it's me because, never mind. I was going to draw my beard in here, but there. You can tell it's me because I've got a beard, and then there's you, right? You can tell it's you because you don't have a beard. So we both want to get from where we are starting up to the top of the mountain. Now, because, I know this mountain, I take a trail that goes right up to the top of the mountain. You, because you're not as familiar with this particular mountain, you take a trail that goes out this way, and then switched back here, and then goes around the backside of the mountain and comes out over here, and you do a little more switching back, and then it goes back around the other side of the mountain, and you eventually make it to the top. Now, state function. The height or altitude change is the same for both of us, right? We have gone the same height. However, I traveled a much, much shorter distance to make that altitude change happen, right? So the altitude change would be a state function, right? A property of the system that is determined by the current conditions, unaffected by the path that was taken, right? So the altitude difference is a state function, but whereas I took a short path and you took the long, winding, scenic path, right? The distance we traveled was very different, but the change in altitude was the same. So that is an example of a state function, and we will come across a few of those in thermodynamics. And in fact, here's one right now. Enthalpy. It is a state function that relates to the flow of heat. It is related to other state functions by the equation H equals E plus PV, which, when I told you it's related to other state functions, means that you should now know that enthalpy, internal energy, pressure, and volume are all state functions, which means that we can combine the functions of internal energy, pressure, and volume to come up with this new thing, enthalpy, or the flow of heat. So hopefully you will remember these kinds of diagrams. I know they're a little blurry here because we talked about these before when we were talking about activation energy and exothermic and endothermic reactions, but now we are going to talk about them in terms of, I'm so glad that this is doing this today. We're going to talk about them in terms of enthalpy, right? And so here, right, this one says energy absorbed, which this is enthalpy, right, or change in enthalpy. And this is energy released, or also change in enthalpy, right? So these quantities here, right, the difference between your starting and ending energy is your change in enthalpy. And the fact whether you are releasing or gaining energy is going to determine whether something is endothermic, right? So endothermic is absorbing energy, and exothermic is releasing energy. And so the change in H, change in enthalpy, is going to determine whether something is endothermic or exothermic. All right, so delta H positive, right, absorbed energy, that is endothermic. Delta H is negative, that is exothermic. Okay, enthalpy of reaction. This can help us to investigate and calculate the energy associated with a chemical reaction. And how we do that is we understand that the enthalpy change is proportional to the amount of reactants consumed in a reaction, which means this that we get to do stoichiometry in our thermo unit. That the enthalpy change for a reaction is equal but opposite to the reverse reaction, and that the enthalpy of a reaction depends on the state of the reactants or products. And like with reaction mechanisms in kinetics, reactions can be combined to form new reactions of interest, and the enthalpies of a reaction can be added together to find the enthalpy change for a new reaction. That is Hess's law. We will deal with that very shortly. So, before we get to some examples, I'm going to stop there for today. I know that was pretty much just all writing and notes, but we will get into some examples in the next video.